Welcome to this lecture entitled The Nature of Uncertainty in Information Theory. Today we will connect uncertainty in artificial intelligence with key information theory concepts. We'll explore how uncertainty arises in AI and how measures like entropy, Kullback-Leibler divergence, and mutual information helps us quantify and reason about that uncertainty. Here's our roadmap. We'll start by defining uncertainty in AI, distinguishing aleatoric versus epistemic uncertainty. Then we'll introduce Shannon entropy, a measure of uncertainty, and explain its connection to file compression. Next, KL divergence as a way to measure how one distribution differs from another, followed by mutual information as a measure of shared information or uncertainty reduction. We'll pause about halfway through for quick recap and transition. In the latter part, we'll apply these ideas to AI in medicine, showing examples in diagnostic decision support, medical imaging, EHR or electronic health records, and genomics. Finally, we'll discuss benefits and limitations, how information theory helps uncertainty quantification in medicine, and where it might fall short. Now that we know our roadmap, let's start with the foundations of uncertainty. First, why should we even care about uncertainty in machine learning or artificial intelligence? In many high-stakes applications, think medical diagnosis or self-driving cars, the cost of an error is huge. If a model is overconfident in a wrong prediction, it can be dangerous. For truly reliable, trustworthy AI, we need to quantify how confident or uncertain a prediction is. In fact, reliable uncertainty estimates are crucial in safety-critical domains. If a model can flag, "I'm not sure about this case," a human expert can step in, or additional data can be gathered. So uncertainty estimation isn't just academic, it's about ensuring that AI decision-making is safer and smarter. Uncertainty in the artificial intelligence domain generally comes from two sources. First is data inherent uncertainty, which is normally called aleatoric uncertainty. Basically, this is the noise or randomness inherent in a process. Second is model or knowledge uncertainty, also called epistemic uncertainty. This comes from our model not having enough information or capacity to perfectly understand the data. It's common to decompose a model's predictive uncertainty into these two components. Why? Because aleatoric uncertainty is like irreducible noise. We can't eliminate it no matter what. Whereas epistemic uncertainty can be reduced by gathering more data or improving the model. Differentiating these two types of uncertainty helps us know what part of the uncertainty we might address versus what part we just have to live with. Let's dive deeper into aleatoric uncertainty. Again, this is the uncertainty stemming from the data or the underlying process itself. It arises from the stochastic nature of the mapping from inputs to outputs. In other words, even if you knew everything and had a perfect model, you still couldn't predict the outcome with certainty because the world itself has randomness or noise inherently inside of it. Think of a medical test with a known false positive rate. There's an inherent randomness in results. Or imagine trying to predict a person's pain level from an X-ray. Pain is a subjective experience and difficult to quantify. Aleatoric uncertainty is irreducible. No amount of additional data will eliminate the fundamental noise. It sets a floor on prediction error. Even the best model will make some errors because of the noise in data or unobserved factors. Next, epistemic uncertainty. This is the uncertainty in the model's knowledge, basically our model's ignorance, and it can be addressed. The model doesn't know what it hasn't seen. Garbage in, garbage out. Formally, it's the uncertainty about the discrepancy between the true data generating process and the model's estimate. This uncertainty is reducible. If you collect more training data, especially covering the troublesome cases, or build a better model, we can shrink epistemic uncertainty. For example, a classifier might be very unsure when it encounters a very rare condition it wasn't trained on. That's epistemic uncertainty. In safety-critical settings, a high epistemic uncertainty is a red flag. It suggests the model might be venturing into the unknown. In practice, we want to handle those cases differently. Maybe ask a human expert or gather more information. Now that we've gone over both types, let's just do a contrast one more time. So aleatoric uncertainty, like I said, is the background or the noise, something you cannot reduce. Epistemic uncertainty, on the other hand, comes from what we don't know. It would go away if we had an infinite data or a perfect model. One quick rule of thumb, if you can't reduce the uncertainty no matter what, it's likely deriving from aleatoric or noise. If throwing more data at the problem reduces the uncertainty, then that remaining uncertainty was epistemic. In any realistic scenario, though, the total uncertainty is a mix of both of these sources. For example, diagnosing a disease, there's aleatoric uncertainty because symptoms might not deterministically map to a disease due to some randomness or patient variability, and epistemic uncertainty because our model might not have seen enough similar cases. We often write total uncertainty equals aleatoric plus epistemic, where we conceptually add these two terms. We'll later see how information theory provides a way to compute such a decomposition. How do we quantify uncertainty in AI and ML models? The central idea is to transition to models that provide probabilistic outputs instead of a single definitive guess. So instead of a rigid class equals cat, the model may output something like 70% cat, 25% dog, or 5% other. That distribution inherently conveys uncertainty. There are a few common approaches to achieve this. Bayesian methods treat model parameters as random variables. A Bayesian neural network, for example, maintains a distribution over its weights, which yields a distribution over its outputs. This natively captures epistemic uncertainty because if the training data is limited, the weight posterior remains broad. However, exact Bayesian training is computationally expensive, so we often rely on approximations like Monte Carlo dropout or deep ensembles. With Monte Carlo dropout, you keep the dropout regularization active at test time and run the network multiple times. Because a different subset of neurons is dropped on each pass, the network behaves like a slightly different model each time, and the variability across these predictions approximates model uncertainty. Deep ensembles approach this by actually training multiple independently initialized models, which brings us to the visualization. This diagram illustrates the architecture of a deep ensemble used for regression tasks. Instead of passing our input, X, through a single network, we pass it through M distinct neural networks in parallel. As you can see at the top of each network, they don't just output a single value. Each individual model outputs the parameters for its own probability distribution, including a mean and a variance. The critical step happens at the mixture level. The individual distributions represented by the blue, purple, and green curves are combined into a single comprehensive Gaussian mixture model, shown by the red curve, with the overall mean and variance. This combined variance is where we see our uncertainty. If the individual networks are highly confident and agree with one another, their predicted means will overlap, resulting in a tight, narrow, combined distribution of low uncertainty. However, if the networks disagree widely because they haven't seen similar data before, their individual means will be spread far apart. This disagreement inherently widens the variance of the final mixture distribution, effectively giving us a mathematical way for the model to say, proceed with caution, I am highly uncertain. Now that we've covered how to quantify uncertainty in practice, let's transition to the mathematical core of the lecture, information theory. Now we introduce our first information theoretic tool, Shannon entropy. Entropy, denoted big H, is the cornerstone concept in information theory. It quantifies the uncertainty or average surprise of a random variable's outcomes. The formula for Shannon entropy, shown on the slide, sums over all possible outcomes X. Think of it this way. If you randomly draw an outcome X, entropy tells you, on average, how many bits of information you gain by learning that outcome. More entropy means each outcome was more unpredictable, so you learn more when it's revealed. This curve on the right maps the entropy of a simple coin flip. Notice how the entropy drops to 0 at the extremes, where the probability is 0 or 1 because the outcome is certain. The curve peaks exactly at 0.5, representing a fair coin with maximum unpredictability, which corresponds to exactly 1 bit of entropy. This visualizes the core rule. Uncertainty is highest when outcomes are equally likely. Importantly, entropy is measured in bits. Assuming we use log base 2, which nicely corresponds to yes-no question units of information, 1 bit of entropy means on average 1 yes or no question would be needed to resolve the uncertainty. As an example, we have a fair coin flip, where H, or entropy, equals 1 bit. This means it takes exactly 1 yes or no question, such as, is it heads, or is it tails, to completely resolve the uncertainty. Now let's look at another example with 4 equally likely outcomes in these 4 different colored balls, 1 through 4. Here, entropy equals 2 bits, which is the equivalent to asking 2 sequential yes-no questions in order to get the outcome. For instance, you could first ask, is the outcome or is the number in the set 1, 2? And if the answer is yes, then you follow up with, is it 1? Or you can say, is it 2? Also, you can ask, is the outcome in the set 3, 4? And then follow up with the second question, is the outcome 3 or is it 4? Either way, there's a chain of 2 yes or no questions. Shannon's first big result, which is a beautiful and practical connection to data compression, was the source coding theorem in 1948, which says that the entropy of a source in bits is basically the ultimate limit of compression. Entropy tells you how many bits on average you'll need per symbol, letter, pixel, measurement, etc., if you compress that source as efficiently as possible. For example, if your data source is truly random, which is max entropy, no compression algorithm can significantly shrink it. It's already full of information. On the other hand, if your data is predictable, which is low entropy, say a text file with lots of repeated letters, you can compress it a lot because there's redundancy. An everyday example, zip or PNG compression algorithms essentially try to remove redundancy. If you compress a file multiple times and it doesn't get any smaller, you've basically approached the entropy limit. So entropy isn't just this abstract mathematical concept. It tells engineers the best case compression ratios for files. It's the reason why you can compress English text, which has lower entropy per character, but you cannot significantly compress truly random data beyond its entropy. Let's ground this in a practical example to see how entropy limits compression. Suppose we have a data source that emits just 4 symbols, A, B, C, and D. However, they don't appear equally. A is very common, appearing about half of the time, so the probability of A is 0.5. B appears 25% of the time, and C and D are rare at 12.5% each. If we ignore these probabilities and just use a standard naive fixed length binary code, we need 2 bits to uniquely identify 4 symbols. We might assign 00 to A, 01 to B, 10 to C, and 11 to D. In this scenario, we are spending exactly 2 bits per symbol, no matter which one appears. But Shannon's source code theorem tells us that we can do better by exploiting the uneven probabilities. We can use a smarter variable length code. Let's give our most common symbol A the shortest code with just a single bit of 0. We'll give B a 2-bit code of 10, and for our rare symbols C and D, we'll use the 3-bit codes 110 and 111 respectively. So how much space did we actually save? To find out, we calculate the expected code length, which is just the weighted average of our new bit lengths. We multiply the probability of each symbol by its new code length. When we sum that up, our expected length is only 1.75 bits per symbol. So by paying attention to the probabilities and allowing these variable length codes, we saved 0.25 bits per symbol on average compared to the naive approach. This perfectly illustrates compression. We squeezed out redundancy by assigning shorter codes to more predictable outcomes. Entropy shows up all over artificial intelligence and machine learning. Firstly, as a measure of predictive uncertainty. If our model gives a probability distribution over classes, we can calculate its entropy. A higher entropy means the model is unsure. The probabilities are spread out. If the entropy is low, the model is confident, or one outcome has most of the probability or mass. Entropy is also the basis of information gain in decision trees. When building a tree, we ask, which feature should we split on? The answer is the one that most reduces entropy of the target distribution. That is, the one that yields the highest information gain. Information gain is used as a split criterion in the famous decision tree algorithms ID3 and C4.5. At each node, they choose the feature and split that maximizes the reduction in label entropy. That is the highest information gain. Next, cross entropy loss, which is commonly used in train classifiers, is derived from entropy. If the true distribution is one hot, 100% one class, and the model gives some distribution Q, the cross entropy H, P, and Q measures the surprise of seeing the true class under distribution Q. Minimizing cross entropy aligns the model's distribution with reality. Finally, in reinforcement learning, we often add an entropy bonus to the policy's objective. This ensures the agent doesn't become overconfident in one action too early. It keeps exploring by favoring higher entropy policies. All these illustrate how entropy serves as a currency of uncertainty. Let's solidify intuition with a few examples of entropy, all using log base 2 so we can measure bits using yes or no questions. For a fair coin flip, there are 2 equally likely outcomes. Thus, the entropy is 1 bit. That makes sense because learning the result of a coin flip gives you 1 bit of information. Is it heads or is it tails? Thus, for a fair coin, you only need 1 yes or no question to resolve. Now for something a little bit more complex. For a specific sequence, like 3 heads in a row, heads, 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 with a fair coin, the probability of that specific outcome is of course 0.5 raised to the third power, or 12.5%. If that event happens, you've seen something a bit unlikely. The information content or surprise level of that outcome is simply the negative log base 2 of 0.125, which brings us back to 3 bits. Since there was 3 coin tosses, each of them worth 1 bit, you add them up, you get 3 bits. That means seeing 3 heads in a row is about as informative of getting 3 independent fair coin flips worth of information all at once. However, let's look at a very rare event. Let's say something that happens 0.1% of the time, so has a probability of 0.001. If that occurs, that's about 9.97 bits, which is the negative log 2 of 0.001. That's a huge surprise, and it's equal to the amount of information you would get from 10 yes or no questions. Entropy would weight such large surprises by their rarity. The key idea here to emphasize is that individual unlikely events are very informative if they occur, but they happen rarely. Entropy takes the surprise and averages it, weighted by how often each outcome occurs. So entropy is the expected information content itself, the average surprise you get when you see the outcome of a random variable. On the last slide, we were still in toy probability land. Fair coins, sequences of heads, and rare events. Entropy and information content there were purely about a distribution over outcomes and how surprising a particular event is. In AI and ML, we want to bring the same ideas over to model predictions. For any input X, we'd like the model to give us a predictive distribution, the probability of Y given X. And then we can ask, what is the entropy of this predictive distribution? How spread out is it? How uncertain is the model about Y for this particular X? The key is this is not specific just to deep learning. Many model families can give us probabilities. Logistic regression and softmax regression directly output class probabilities. We can compute entropy of these probabilities as a measure of uncertainty. Probabilistic classifiers like naive Bayes or generative models model the probability of Y given X and the probability of Y and give the probability of Y given X via Bayes' rule. Tree-based models such as random forest or boosted trees often give class probabilities as fraction of trees voting for each class, which we can treat as the probability of Y given X and compute entropy on. Bayesian models, in general Bayesian linear and logistic regression, Gaussian processes, Bayesian additive regression trees, etc., naturally produce predictive distributions with credible intervals or full posteriors. On top of that, we have some general tricks for epistemic uncertainty, like ensembles and bagging, where any model class can be ensembled, trees, linear models, neural nets. If the members of an ensemble disagree strongly on a prediction, that suggests high model uncertainty. Bayesian approaches, again, not just neural networks, look for, instead of one best set of parameters, keep a distribution over parameters and integrate over it to get a predictive distribution. MC dropout and deep ensembles, which we talked about in the last slide as well, and which we also visualize here, are specialized versions in neural networks of the same general idea, where you get multiple plausible models, as you see in the image here, and look for how much their predictions vary. So the conceptual move from the previous slide to here is, we looked at the entropy of a simple distribution, coins, rare events. Now we want entropy of the model's predictive distribution, probability of Y given X, and there are many model-based ways, not only deep learning, to obtain that distribution. Once we have the probability of Y given X, all the information theoretic machinery, entropy, Kullback-Leibler, divergence, mutual information, applies directly to uncertainty in AI predictions. So far, we focused on entropy, which quantifies uncertainty of a single distribution. But in AI, we frequently need to compare distributions or assess the value of information. For example, how much did our uncertainty drop after seeing new data? Or how different is the model's predicted distribution from the true distribution? For these questions, we introduced 2 more concepts: Kullback-Leibler, or KL divergence, and mutual information, or MI. KL divergence is essentially a way to measure the difference between 2 distributions. It tells us in information terms how inefficient it is to use one distribution to describe another. Mutual information, on the other hand, tells us how much knowing one random variable, say a test result, informs us about another random variable, say the diagnosis. These will let us quantify information gain and uncertainty reduction formally. In the next section, we'll define KL divergence and mutual information and see how they relate back to uncertainty. Let's quickly pause for a brief recap for the first part of this presentation. We saw that uncertainty in AI comes in 2 flavors: aleatoric, which is the inherent noise in data we can't get rid of, and epistemic, which is the uncertainty from the lack of knowledge, which more data or a better model could reduce. We then introduced Shannon entropy, which quantifies the uncertainty of a random variable in bits. Uniform distributions have high entropy, lots of uncertainty, while skewed distributions have lower entropy because one outcome kind of dominates. Entropy turned out to have deep connections. It's literally the theoretic limit of compression, which means you can't compress below entropy in bits. And it underpins techniques like information gain in decision trees and cross-entropy loss for training classifiers. With these concepts established, we're now ready to extend to KL divergence and mutual information, which will allow us to talk about differences between distributions and how much information new data provides. This will pave the way to understanding uncertainty in a more dynamic sense and will set us up for applications in the second half of the lecture. We have just recapped how entropy measures uncertainty within a single distribution, but what happens when we need to compare two different distributions or understand how they interact? Let's talk about KL divergence and mutual information. KL divergence. This is a central quantity in information theory and machine learning that measures how different two probability distributions are. Think of P and Q as two distributions over the same set of outcomes. In most AI and ML contexts, we interpret P of X as the true or target distribution, how the data are actually generated, and Q of X as an approximation, what our model assumes or predicts. You can think of this as an expectation under P of the log difference between P and Q. A few key properties of KL divergence are worth spelling out. First, the KL divergence from P to Q is always greater than or equal to 0. It is exactly 0 if and only if P and Q are the same distribution. So if there's any mismatch between P and Q, the KL divergence is strictly positive. Second, KL divergence is asymmetric. In general, the KL divergence from P to Q is not the same as the KL divergence from Q to P. Because of that asymmetry, we call it a divergence rather than a true distance or metric. To understand the intuition, imagine that the real world actually follows the distribution P. Events are drawn according to P. But if you design a model under the assumption that the world follows Q instead, in that setting, the KL divergence from P to Q tells you how many extra bits per symbol you waste on average because you use the wrong assumption Q instead of the true distribution P. If Q is a very good approximation to P, then for most outcomes X, the ratio P of X over Q of X is close to 1. The logarithm of that ratio is close to 0 and the KL divergence stays small. In other words, your model is almost as efficient as if you had known P exactly. If Q is a poor approximation, for example, if it assigns very low or even 0 probability to events that actually happen under P, then the log of that ratio becomes large in magnitude, and the KL divergence becomes large. In extreme cases where Q assigns 0 probability to an event that P thinks is possible, the divergence can blow up towards infinity, reflecting a catastrophic mismatch between your assumptions and reality. So the way I would summarize this for you is, mathematically, KL divergence is the expected log difference between the true distribution P and the model distribution Q, taken with respect to P. Intuitively, it measures the inefficiency or penalty you pay for pretending Q is true when the data are actually generated from P. KL divergence is used regularly in machine learning and artificial intelligence. First, let's go over model training for classification. When we train a classifier with cross-entropy loss, what we are effectively doing is minimizing the KL divergence from the true label distribution to the model's predicted distribution. Think of the true distribution as a one-hot vector that puts all its mass on the correct class. Think of the model's output as the predicted probability distribution over classes. Minimizing cross-entropy pushes the model's predicted distribution to get closer and closer, in the KL sense, to that true one-hot encoded distribution. Second, let's go over variational inference. Variational inference is a method for approximating complicated Bayesian posteriors. We choose a family of simpler distributions, usually written as Q of theta, and then we minimize the KL divergence from Q of theta to the true posterior distribution of theta given that data. In other words, we are searching over candidate Q distributions to find the one that is closest, in KL divergence to the true posterior. That's how we get a tractable approximation. Third, let's go over variational autoencoders, VAEs, and related generative models. The image is here to assist. In a VAE, there is an explicit KL divergence term in the loss, represented in the middle of the figure. That term penalizes the divergence between the learned latent distribution for the data and some prior distribution in the latent space, often a standard normal. Intuitively, that KL term acts as a regularizer. It keeps the latent representations from drifting too far away from the chosen prior and encourages a well-behaved latent space. More broadly, whenever we want to measure how well a model distribution approximates a target distribution, KL divergence is a natural choice. It appears in comparing generative models to real data distributions, Many reinforcement learning algorithms where policy updates are sometimes constrained by a KL divergence to avoid changing the policy too abruptly, and other places where distance between distributions is the main object of interest. Finally, it's worth noting that sometimes we need a symmetric notion of distance. KL divergence is asymmetric, so in some applications, people use symmetrical versions of KL divergence, such as Jensen-Shannon divergence. For example, generative adversarial networks use an objective related to Jensen-Shannon divergence between the real data distribution and the generator's distribution. The punchline here is that KL divergence is the workhorse for comparing probability distributions in AI. It's embedded in loss functions, in approximate Bayesian methods, in generative models, and even in some reinforcement learning algorithms. Let's illustrate KL divergence in a medical context with a diagnostic test example. Imagine we start with a pre-test probability of disease of about 10% based on symptoms, prevalence, or risk factors. That gives us a prior distribution over two outcomes: disease with probability 10% and no disease with probability 90%. Then we order a diagnostic test and observe a specific result. Say the test comes back negative. Using that result, we update our belief and get a post-test probability of the disease. For example, it might drop from 10% down to 1%. That gives us a new posterior distribution: disease with probability 1% and no disease with probability 99%. KL divergence gives us a way to quantify how much that single test result changed our belief. In this slide, when we write the KL divergence from posterior to the prior, we mean measure how different the posterior distribution over disease and no disease is from the prior distribution over disease and no disease. If the test barely changes our belief, for instance, if the disease probability moves only from 10% to 9%, then the prior and the posterior distributions are almost the same. In that case, the KL divergence is very small, meaning the test result carried little information. If the test result causes a large shift, for example, from 10% to 1%, or from 10% all the way up to 80%, then the prior and posterior distributions are very different. In that case, the KL divergence is larger, telling us that this particular test outcome was highly informative for this patient. Mathematically, in this simple two-outcome setting, you can compute the KL divergence directly from the prior and posterior probabilities of disease and no disease. Clinically, we usually talk about things like sensitivity, specificity, and likelihood ratios, but KL divergence gives a more general information theoretic measure. It tells us how many bits of information this specific test result provided. One final point. This example is about the information carried by one realized outcome of the test for a given patient. When we move to planning or evaluating tests more generally, we will often be interested in the expected information gain averaged across all possible test outcomes. That notion of expected information gain leads us directly into mutual information, which we will talk about next. Mutual information is another key quantity in information theory. Intuitively, it answers the question, how much information does one random variable tell about another? On this slide, you see one definition. The mutual information between x and y equals the entropy of x minus the entropy of x given y. In words, that is the reduction in uncertainty about x once you observe y. Because mutual information is symmetric, you can equally write it as the entropy of y minus the entropy of y given x, which is the reduction in uncertainty of y once you observe x. You can always express mutual information as the entropy of x plus the entropy of y minus the joint entropy of x and y. That form makes the symmetry very explicit and gives a nice picture. If you imagine a Venn diagram, like the one we have on this slide, with one circle for the entropy of x and one circle for the entropy of y, the overlap between those circles is the mutual information. That overlap is the information they share. A few key properties to keep in mind. Mutual information is always non-negative. It is zero if and only if x and y are independent, because in that case, knowing one does not reduce uncertainty about the other at all. Imagine instead of a Venn diagram, you just have two independent circles. It reaches its maximum when one variable completely determines the other. So that would be a completely overlapping Venn diagram. For example, if y is a deterministic function of x, then once you know x, you have no uncertainty left about y. And the mutual information between x and y equals the entropy of the less uncertain variable. In that sense, you have gained all of that variable's bits of uncertainty. Mutual information is measured in bits, just like entropy. You can think of it as how many bits of x are revealed on average when you observe y. And because it's symmetric, the same number of bits of y are revealed when you observe x. It's also useful to contrast mutual information with correlation. Correlation is a very specific measure that mainly captures linear relationships. Mutual information, by contrast, can capture any kind of dependency, including nonlinear and even very strange relationships, as long as knowing one variable changes the distribution of the other. So the big takeaway, mutual information is a measure of shared information or connection strength between variables in information theoretic terms. It is always non-negative, it is symmetric, and it drops to zero exactly when the variables are truly independent. Now that we have an intuition for mutual information as how many bits about X we learned from Y, let's look at where it shows up in machine learning and artificial intelligence. First, feature selection and feature importance. One simple strategy is, for each feature, compute the mutual information between the feature and the target, and then select the features with the highest mutual information. Or, in post-analysis, use mutual information as a feature importance criterion. In our earlier terms, that means we pick the feature that most reduce the entropy of the label when we observe them. This is more general than correlation because mutual information can detect any dependency, not just linear relationships. In a biomedical setting, that might mean picking lab values, vital signs, or imaging derived features that carry the most information about an outcome like mortality, readmission, disease state, or length in hospital. Second, clustering and dependency discovery. Mutual information can be used as a measure of how strongly two variables are related. If two signals share high mutual information, knowing one substantially reduces uncertainty about the other. In practice, you can build a similarity matrix based on mutual information and then cluster variables that share a lot of information. In multimodal biomedical data, for example, you might find that certain lab tests, diagnoses, and medications group together because they share high mutual information, revealing clinically meaningful structure. Third, active learning. In active learning, we do not label all data up front. Instead, we choose which unlabeled sample to label next. A more advanced strategy uses mutual information between the model's parameters and the potential label. In other words, we pick the sample whose true label would, if we knew it, most reduce the model's uncertainty. So mutual information here is used as an expected entropy reduction criterion. Which query would give us the biggest information gain about the model? Fourth, neural networks and deep generative models. In deep learning, mutual information shows up in several areas. It shows up in methods like InfoGAN, where we add a mutual information term between a part of the latent code and the generated data. The goal is to force certain latent dimensions to have high mutual information with interpretable aspects of the output. For example, digit identity, rotation, or style. So those dimensions become meaningful factors rather than arbitrary noise. In the information bottleneck perspective, we view a neural network layer as trying to compress the input representation to reduce its entropy, while still retaining as much mutual information with the target as possible. So again, entropy and mutual information are used together. Compress away what is not useful, keep what is informative about the output. Big picture is, mutual information gives us a unifying way to talk about what is informative, which features are informative about the label, which variables are related to each other, which data points would be most informative to label next, and which parts of a learned representation carry information about clinically relevant endpoints, or any endpoint. Now let's revisit the medical testing scenario, but this time from the perspective of mutual information instead of KL divergence. Earlier with KL divergence, we focused on one specific test result and asked, how much did this particular outcome change our belief? Mutual information steps back and asks a slightly different question. On average, over all possible test results, how much does this test reduce our uncertainty about disease status? That is exactly what we mean when we say the mutual information between disease and test is the expected reduction in uncertainty about disease from knowing the test result. Using the notation on the slide, the mutual information between disease and test equals the entropy of disease before we run the test minus the entropy of disease after we condition on the test result, averaged over all possible test outcomes. In other words, the first term, the entropy of disease, is our baseline uncertainty in whether the patient has the disease before testing. The second term, the entropy of disease given test, is the remaining uncertainty once we have seen the test result, averaged over the distribution of possible test outcomes. This leads to a very natural interpretation. If a test is perfect, it always correctly identifies whether the disease is present or absent. Then once we see the result, there's essentially no uncertainty left about disease status. In that idealized world, the entropy of disease given test would be zero, and the mutual information would equal the full entropy of disease. In other words, the test has extracted all the uncertainty we initially had. At the other extreme, if the test is useless, it never changes our probabilities at all. Then our uncertainty about disease after seeing the test is the same as before. In that case, the entropy of the z's given test equals the entropy of the z's, and the mutual information is 0. The test provides no information on average. Practically, we can use mutual information to compare tests. Suppose test A, when we compute the mutual information between the z's and the test result, yields about 0.2 bits of information on average, while test B yields about 0.5 bits. Then test B is expected to reduce our uncertainty more. It is, in that sense, the more informative test. Clinically, this gives us a way to formalize the value of a diagnostic test in information theoretic terms. It lines up with intuition. Tests that tend to produce large shifts in our disease probabilities, like highly sensitive or specific tests, will have higher mutual information. Tests that usually leave our probabilities near unchanged will have low mutual information. So, mutual information here plays a role very similar to expected information gain. In decision analysis, it tells us in bits how much diagnostic uncertainty a test is expected to resolve, and that can guide which test we might want to order. Now let's connect information theory back to the two types of uncertainty we discussed earlier, aleatoric and epistemic. The starting point is the predictive distribution of the model. For a given input, x, our model gives us a probability distribution over possible outputs y. The entropy of that predictive distribution is our total predictive uncertainty for that x. In other words, we measure how spread out the probabilities over y are. The more spread out, the higher the entropy, and the higher the uncertainty. In a Bayesian model, or in an ensemble of models, this predictive distribution is obtained by averaging over different possible parameter settings or different members of the ensemble. Information theory gives us a way to decompose that total uncertainty to two parts that correspond nicely to aleatoric and epistemic uncertainty. The first part corresponds to aleatoric uncertainty. Imagine you somehow knew exactly which model parameters were correct, or exactly which ensemble member was the true one. Even then, for a noisy medical problem, there would still be some remaining uncertainty in the prediction because of inherent randomness in the data. Remember, we can never remove aleatoric uncertainty. For each fixed set of parameters, you can measure the entropy of the output distribution given x and those parameters. If you then average that conditional entropy over the posterior distribution of parameters, you get a quantity that reflects the expected uncertainty due to just noise and randomness. That is what we interpret as the aleatoric component. The second part corresponds to epistemic uncertainty and is captured by a mutual information term. Specifically, you can look at the mutual information between the output y and the model parameters, conditioned on the input x and the observed data. Intuitively, this mutual information measures how much learning the true value of y would tell us about which parameter settings are plausible. If all parameter settings in the posterior produce essentially the same predictive distribution over y, then knowing y does not tell us anything new about the parameters. In that case, this mutual information is essentially 0, and epistemic uncertainty is actually low. If different plausible parameter settings disagree strongly about y, then observing the true y would sharply narrow down which parameters are compatible with the data. In that case, the mutual information is large, and epistemic uncertainty is high. Mathematically, under the usual assumptions for Bayesian predictive distributions, you can show that the entropy of the predictive distribution can be written as the expected conditional entropy over parameters plus this mutual information term between y and the parameters. In other words, total predictive uncertainty equals average uncertainty due to data noise plus additional uncertainty coming from not knowing which model parameters are correct. This additive decomposition has been popularized in the machine learning literature and is widely used as a conceptual and practical way to separate aleatoric and epistemic uncertainty in Bayesian deep learning and in ensembles. However, it is worth a note of caution. More recent work points out that the neat split is not always perfectly clean. In some situations, the boundary between what we call aleatoric and epistemic can blur, and the decomposition might not fully match our intuitive "what if we collected more data" interpretation. Even with those caveats, this information theoretic view is very helpful. It gives us a principled way to talk about how much our predictive uncertainty is due to irreducible noise in the data versus how much is due to our limited knowledge of the model or parameters. To wrap up this section, let's step back and ask, why bother with entropy, KL, and mutual information at all when thinking about uncertainty in AI or ML in medicine? First, there is a principled framework. We are not inventing ad hoc scores for uncertainty. Information theory gives us precise mathematical definitions of uncertainty and information that come from Shannon's axioms. Entropy quantifies uncertainty. KL divergence quantifies how different two distributions are, while mutual information quantifies how much one variable tells us about another. These are not arbitrary choices choices, they have clear, well-established interpretations. Second, these measures are unified and domain agnostic. A bit is a bit, whether we're talking about uncertainty in medical diagnosis, uncertainty in a language model's next token, or uncertainty in a computer vision model's prediction. The same entropy, KL divergence, and mutual information apply across different data types and different models. That makes it easier to transfer ideas and tools from one domain, like communication theory or NLP, like clinical decision support. Third, there are deep theoretical links to learning and generalization. Information theoretic quantities appear in results that connect how much a model memorizes the training data to how well it generalizes. For example, if the mutual information between the model parameters and the training data is very large, that suggests that the model has encoded a lot of specific detail about the training set, which can be a warning sign for overfitting. In contrast, models that capture just the right amount of information about the data can generalize better. So these measures are not just descriptive, they show up in generalization bounds and learning theory. Finally, they have a strong track record for practical success. We have already seen several examples. Decision trees use entropy or information gain to choose splits. Standard classification networks are trained with cross-entropy loss, which is directly related to KL divergence between the true and predicted label distributions. Variational autoencoders and other generative models use KL divergence as a regularization term on latent variables. Active learning strategies and some deep generative models use mutual information to decide which data points are most informative or which representations are most meaningful. The fact that these tools keep reappearing, from classical models like decision trees to modern deep learning and Bayesian methods, shows that information theoretic measures are not just elegant mathematically. They also improve performance, help calibration, and give us a quantitative handle on uncertainty that we can design, optimize, and reason about in a principled way. Up to this point, we've focused on the strengths of information theoretic measures, but it's important to be honest about their limitations, especially when we start using them to separate aleatoric and epistemic uncertainty. First, there is growing evidence that the popular practice of defining aleatoric uncertainty as an average conditional entropy and epistemic uncertainty as a mutual information term can behave incoherently in some settings. Recent analyses have shown examples where this decomposition gives results that do not line up with our intuitive understanding of data noise versus model ignorance. In other words, the math is valid, but the interpretation can be questionable in certain models or edge cases. Related to that, the neat-looking additive formula says total predictive uncertainty equals aleatoric plus epistemic relies on fairly idealized assumptions. Outside of these assumptions, the split can lose its meaningfulness. The numbers you get for the aleatoric and epistemic pieces might not behave in ways that match how a clinician or a modeler would naturally think about what is reducible versus irreducible uncertainty. A second limitation is more general. Entropy is an average measurement that can hide structure in the uncertainty. Two very different predictive situations can have exactly the same entropy. For example, consider a model that spreads probability evenly over 10 different possible diagnoses versus a model that is generally torn between just 2 diagnoses at 50-50. Both can yield similarly high entropy values, but they feel different from a decision-making perspective. In the 10 class case, the uncertainty is very diffuse, and it may signal that the problem is inherently ambiguous or that the model has very little idea what's going on. In the 2 class case, the uncertainty is concentrated between 2 plausible options, and one additional strong test or feature might quickly resolve the ambiguity. Entropy alone does not distinguish between these types of uncertainty, even though they have different implications for action. The bottom line here is entropy, KL divergence, and mutual information are powerful, principled tools, but they are not a complete description of uncertainty. If we apply them mechanistically, especially when decomposing uncertainty in aleatoric and epistemic parts, we can be misled. In complex medical settings, we often need to combine these information theoretic measures with other diagnostics, domain knowledge, and practical considerations about what kinds of uncertainty are most concerning for patient care. While entropy-based measures have theoretical limitations, there are also practical hurdles to implementing them. In this next section, we will cover the practical challenges of using these information measures in AI and ML. We will also explore how we can actively use uncertainty to guide our data collection through a process known as active learning. So far, information theoretic measures look very attractive, but there are some practical challenges when we try to use them in real-world application. First, calibration. All of these measures assume the model's predicted probabilities are meaningful. If a model is overconfident, often predicting very high or very low probabilities but being wrong a lot, then the entropy can be low while the model is actually unreliable. In that case, entropy or KL will falsely suggest high confidence, We often need calibration tools like reliability diagrams or temperature scaling before we can trust entropy as a measure of uncertainty. Second, interpretability for users. Telling a clinician the model has 0.7 bits of uncertainty is not very helpful. They want to know why the model is uncertain. Is it because the data are noisy, or because the model has seen very few patients? A single entropy value does not explain whether the uncertainty is aleatoric, epistemic, or something else, so it can feel opaque to end users. Third, not all uncertainty is equal in practice. Information theory treats 1 bit of uncertainty as 1 bit, regardless of context, but clinically, 1 bit about cold versus flu is very different from 1 bit about cancer versus no cancer. The consequences and risk are totally different, and entropy by itself does not encode that. We need domain knowledge and utility or cost considerations to weigh uncertainty appropriately. Finally, workflow integration. Even if we can compute good uncertainty scores, deciding how to use them is non-trivial. For example, we might say, if entropy exceeds some threshold, trigger a human review or override. But choosing that threshold, validating it prospectively, and making sure it fits into real clinical workflows is hard. Too low a threshold and everything gets flagged. Too high and we miss dangerous cases. So information theoretic measures are powerful tools, but they are not plug and play. We need calibration, careful interpretation, awareness of clinical context, and thoughtful integration into decision pipelines that make them genuinely useful in medicine. Now let's look at how uncertainty can actively drive data collection, not just model evaluation. In active learning, the model does not passively accept a fixed labeled dataset. Instead, it looks at a pool of unlabeled examples and asks, which one should I label next in order to learn the most? A simple strategy is uncertainty sampling. Choose examples where the model's predictive distribution has high entropy or otherwise indicates high uncertainty. The idea is that labeling these cases will most quickly reduce epistemic uncertainty. A more principled version of this is BALD, Bayesian Active Learning by Disagreement. BALD selects the unlabeled example that maximizes the mutual information between the model parameters and the unknown label. In plain language, it asks, for which example would knowing the true label most reduce our uncertainty about the model itself? These are typically borderline or ambiguous cases where different plausible models disagree. Labeling these cases gives us the largest expected information gain about the parameters. The benefit is data efficiency. We do not spend human labeling effort on examples the model is already very sure about. Instead, we focus on a small set of confusing examples that will most improve the model when labeled. In a medical setting, imagine an AI-based triage or imaging system. It could run on a large stream of cases, but specifically request expert labels only for cases where its predicted probabilities have high entropy or the mutual information base score is high. Those are the cases where the model is unsure and where a radiologist or clinician's labels would be most valuable, both for safety in the moment and for improving the model on difficult, high-risk cases. I want to briefly connect cross-entropy loss back to KL divergence, just to underline how deeply information theory is built in standard practice. On this slide, you see the relationship between cross-entropy and KL divergence written as the entropy of P and Q equals the entropy of P plus the KL divergence from P to Q. In other words, the cross-entropy between two distributions P and Q is equal to the entropy of P plus the KL divergence from P to Q. In a classification setting, we usually think of P as the true label distribution and Q as the model's predicted probabilities. For a single training example with one correct class, that true distribution is effectively one hot. Probability 1 on the correct class and 0 on the others. For that one hot distribution, the entropy of P is 0 because there is no uncertainty about the true label. That means that, for classification, the cross-entropy between P and Q is essentially just the KL divergence from the true distribution to the model's predicted distribution. When we minimize cross-entropy loss during training, we are effectively minimizing that KL divergence. We are pushing the model's predicted probabilities to get as close as possible to the true label distribution. This is why cross-entropy is such a natural loss function. It is directly rooted in information theory. It penalizes the model whenever its predicted distribution disagrees with the true distribution, in proportion to how inefficient it would be to encode true labels using the model's probabilities. When the model is very wrong, assigning low probability to the correct class, the cross-entropy and therefore the implied KL divergence is large, which produces a strong gradient to correct the model. So when we say we train a classifier with cross-entropy loss, under the hood we are using Shannon-style information measures to force the model to speak the same distribution as the data, in other words, the same language. This connection is not an accident. It also falls out naturally from maximum likelihood estimation. It is a nice example of information theory and statistical principles aligning with practical, effective training objectives. Calibration is a practical but critical aspect of uncertainty. A model is well calibrated if its predicted probabilities match what actually happens. For example, among all patients for whom the model says 90% probability of disease, roughly 90% should in fact have the disease. If only half do, the model is clearly overconfident. This matters because an overconfident model can output very low entropy predictions, probabilities close to 0 or 1, while still being wrong a lot of the time. In other words, the entropy looks low, but the model does not deserve that level of confidence. In medicine, that can be dangerous. The model may fail to signal uncertainty in cases where clinicians really should be cautious. On the other side, a model can be underconfident, assigning middling probabilities like 60% almost everywhere. That leads to higher entropy but is not very actionable. It never clearly commits, even when it's usually right. To address this, we often apply calibration methods after training. Examples include temperature scaling, which rescales the model's logits to soften or sharpen the probabilities without changing which class is ranked highest; Platt scaling, which fits a simple logistic regression on the model scores; isotonic regression, a non-parametric method for adjusting probabilities. These techniques do not typically change accuracy, but they adjust the confidence levels so that the predicted probabilities better align with observed frequencies. Once a model is well calibrated, its entropy-based uncertainty becomes more trustworthy. When it says, "I'm 90% sure," we can interpret that as, there is about a 10% chance this is wrong, which is exactly the kind of quantitative uncertainty a clinician can reason with, whether to order more tests, seek a second opinion, or accept the model's recommendation. Before we move on, let's quickly summarize the core information theoretic quantities we've been using. First, entropy. Entropy of X is our basic measure of uncertainty for a single random variable. It reflects the expected surprise in bits. High entropy when X is spread out and unpredictable, low entropy when X is concentrated and more certain. Second, KL divergence. The KL divergence from P to Q compares two distributions. It is 0 only when P and Q are the same, and it tells us how many extra bits on average we would need if we encoded data that truly followed P using a code that assumes Q instead. So it measures how wrong Q is as a model of P. Third, mutual information. Mutual information between X and Y measures how much they share in terms of information. It is the reduction in uncertainty about X when we know Y, and symmetrically, the reduction in uncertainty of Y when we know about X. It is 0 when they are independent and grows as their dependency increases. Again, use the Venn diagram as a visualization. There are also a few key relationships to keep in mind. The chain rule of entropy says that the joint entropy of X and Y equals the entropy of X plus the conditional entropy of Y given X. In other words, total uncertainty about the pair can be split into uncertainty about X plus the remaining uncertainty about Y once X is known. Mutual information can be written as the entropy of X plus the entropy of Y minus the joint entropy of X and Y. That form makes it clear that mutual information is the overlap between their information. Cross entropy between two distributions P and Q can be written as the entropy of P plus the KL divergence from P to Q. That identity links our classification loss directly to KL. Training with cross entropy is effectively minimizing the divergence between the model's predicted distribution and the true label distribution. These quantities, entropy, KL divergence, and mutual information, and these relationships form the backbone of how we think about uncertainty and information. With them in hand, we can now more clearly see how AI systems in medicine quantify uncertainty, where they may fail, and how we might use these measures to design safer, more informative models. Let's quickly recap what we've done in this second part of the lecture before we fully move to medical context. We started with entropy and then extended our toolkit with KL divergence and mutual information. KL divergence gives us a way to measure how far one distribution is from another. In practice, that means how far the model's predicted distribution is from the true distribution, and we saw that this sits directly underneath common training losses like cross entropy. It also lets us quantify how much a belief update, like a diagnostic test result, has shifted our distribution over disease states. Mutual information measures how much knowing one variable reduces uncertainty about another. That makes it a natural tool for deciding which features are informative, which data points to label in active learning, and how much information a diagnostic test provides on average. Then we looked at how, in a Bayesian or ensemble setting, predictive uncertainty can be decomposed into two parts using these tools: an aleatoric component that reflects expected noise or randomness in the data, and an epistemic component that reflects model uncertainty, often expressed as a mutual information term between outputs and parameters. We also emphasize that this decomposition, while elegant, must be used carefully because it can behave strangely in more complex models or edge cases. On the positive side, information theory gives us a rigorous general framework for talking about uncertainty with quantities that are mathematically well-defined and widely applicable across domains and model classes. On the cautionary side, bits of uncertainty are not automatically intuitive for end users, entropy-based decompositions can be misleading if applied blindly, and we still need good calibration and thoughtful communication for these measures to be useful in practice. With that toolkit in place, we now shift fully into AI in medicine. In medicine, uncertainty is not an abstract concept. It is central to differential diagnoses, test ordering, and treatment decisions. For medical AI systems to be trusted and safe, they need to represent, communicate, and manage uncertainty in a way that aligns with clinical reasoning. In the next part, we'll see how entropy, Calibration, and mutual information show up in diagnostic support, imaging, and other medical applications, and how they can both help and complicate real-world healthcare AI. For the final section of the lecture, we will look at how all of this is applied in the real world, specifically medical applications. In the medical domain, uncertainty is a first-class concern. There's a famous quote from Sir William Osler: "Medicine is a science of uncertainty and an art of probability." Clinicians routinely think in probabilistic terms. What is the chance of this diagnosis given these symptoms? How much does this lab result change the odds? What is the risk of a complication? They manage and communicate uncertainty every day. Because of that, a model in healthcare that cannot express uncertainty is problematic. Doctors are understandably reluctant to trust a black box that says, "This is cancer," with no sense of confidence, especially if it could easily be wrong. If instead the AI says, "This looks like cancer with about 70% probability," a clinician can work with that. They might order more tests, seek a second opinion, or treat more cautiously, depending on how much residual uncertainty remains. The stakes are high. False confidence can be dangerous. We would prefer a model that sometimes says, "I'm not so sure about this case," when it encounters something novel or ambiguous, instead of one that always returns a confident label regardless of its internal uncertainty. Information theory provides a language and toolkit for this. Entropy lets us quantify how uncertain a diagnostic prediction is, and mutual information helps formalize how much a new test or piece of evidence is expected to reduce that uncertainty. Those concepts map naturally onto things clinicians already understand, like how a test result changes pre-test to post-test probability. Using these tools, we can design AI-based clinical decision support systems that not only make predictions, but also reason about and communicate their own uncertainty, making them more trustworthy collaborators in patient care. Now let's see how these information theoretic ideas map onto diagnostic decision support. Start with a typical clinical situation. A patient comes in and we have a differential diagnosis, a list of possible diseases, each with some probability. That set of probabilities forms a distribution over diagnoses, and its entropy tells us how uncertain we are overall. If many diagnoses are roughly equally likely, the entropy is high. If one diagnosis dominates, the entropy is low. Next, we consider diagnostic tests, blood work, imaging, cultures, and so on. Each test result leads us to update the diagnosis probabilities using Bayes' rule. Information theory lets us quantify how informative a particular test result was. We can compare the pre-test distribution of diagnoses to the post-test distribution and use Calibration from the posterior to the prior as a measure of how much that single result shifted our belief. If a test changes the probability of a key disease from, say, 10% to 80%, that corresponds to a large Calibration, a big information update. If probabilities barely move, the Calibration is small, meaning that particular result did not contribute much information. When we are choosing which test to order next, we look ahead. Instead of focusing on one realized result, we consider all possible outcomes and their probabilities. The expected information gained from a test is exactly the mutual information between the disease variable and the test outcome. So we can compute the mutual information between disease and test and choose the test with the highest value. In other words, we pick the test that, on average, is expected to reduce our diagnostic uncertainty the most. This lines up with clinical intuition. A good test is one that sharply separates the remaining plausible diagnoses, not one that leverages everything almost unchanged. Entropy measures how confused we currently are. Calibration tells us how much a specific test result reduced that confusion, and mutual information tells us which test is worth doing in the first place. In medical imaging, ML, and AI, including radiology, pathology, dermatology, and ophthalmology, uncertainty is especially important because these systems are increasingly used to support high-stakes decisions like detecting tumors or acute findings. For segmentation tasks, such as outlining a tumor, modern models can output a probability map for each pixel rather than a hard mask. For each pixel, we can look at the entropy of that predicted distribution over classes. For example, tumor versus non-tumor. Regions where the entropy is high are regions where the model is unsure about the boundary. Those high-entropy pixels can be highlighted to the radiologist as uncertain areas that warrant closer inspection. For classification tasks like predicting pneumonia versus no pneumonia from a chest x-ray, we again look at the predictive distribution. If the model's probabilities are very peaked, say extremely close to 0 or 1, that suggests low entropy and high confidence. If they are closer to a 50-50 split, the entropy is high, signaling that the model is undecided. When we use ensembles or Monte Carlo dropout, we can also examine the variability of predictions across different runs or models to gauge epistemic uncertainty. Large spread across runs suggests the model itself is unsure, or that the case may be out of distribution relative to the training data. In practice, methods like MC dropout and deep ensembles are widely applied to imaging models to obtain these uncertainty estimates. They allow the system not only to produce a label or a segmentation, but also to flag cases in regions where its predictions should be treated with caution or explicitly double-checked by a human expert. This supports a workflow where the model can say, here's my prediction, but I'm not very confident in this area or in this image, which is far safer and more clinically useful than blind, uncalibrated confidence. Electronic health records, or EHR, are a rich but messy source of information. Longitudinal labs, medications, diagnoses, visits, notes. When we try to predict outcomes like readmission, disease onset, or complications from this data, there is a lot of uncertainty because the information is incomplete, noisy, and patients vary widely. Information theory has been used to ask a basic question: how predictable are patient trajectories? One way to study this is through the entropy rate of disease histories, treating each patient's sequence of diagnoses as a string and estimating how random these sequences are. If the entropy rate is high, the sequence is hard to predict. If it is lower, there is more structure to exploit. Studies that explicitly model temporal order, for example using Markov-style disease transition models or n-gram-like sequence models, have shown that including time information can substantially reduce the entropy of these sequences and increase the theoretical upper bound on predictability. In one analysis, accounting for temporal dependencies increased the predicted upper bound on how well we can forecast future diagnoses from around 12% to nearly 30%. In practical terms, this means that recognizing common progression pathways such as obesity, often preceding diabetes or hypertension, reduces our uncertainty about what might happen next. For machine learning, the message is that models which explicitly leverage longitudinal structure, Markov models, recurrent neural networks, temporal transformers, are effectively extracting more information from EHR sequences and thereby reducing predictive entropy compared to models that ignore time. Information theoretic measures often give us a way to quantify that gain. In deployment, we can also attach uncertainty estimates to patient-level predictions, such as predictive entropy or confidence intervals on risk scores. So clinicians not only see a risk estimate, but also how stable or uncertain that estimate is, helping them gauge how much to trust a given forecast for a specific patient. Genomics is another area where uncertainty is everywhere and information theoretic ideas are already built in. First, genomic data are high dimensional and noisy. Large sequencing panels and whole genomes reveal many variants, but only a fraction is truly pathogenic or clinically relevant. That creates substantial uncertainty about which variants matter for disease risk or drug response. Entropy is used directly to describe genetic diversity and sequence variability. For example, in viral genomes, we can look at the distribution of nucleotides at each position across a viral population within a patient. High entropy at a position means many different bases are observed there, high diversity and high uncertainty. Low entropy means that position is highly conserved. Those conserved low entropy regions are often functionally important and can be attractive drug or vaccine targets because the virus cannot easily mutate them without losing fitness. In precision medicine, we can also think in terms of information gain. How much does adding genomic data reduce our uncertainty about a diagnosis, prognosis, or drug response beyond what we know from clinical features alone? In information theoretic terms, that's asking about the mutual information between genomic features and the clinical outcomes. If knowing a patient's genotype sharply changes our predicted risk or likely treatment response, then the genomic data are providing substantial information. Practical genomics tools make this explicit. Sequence logos in bioinformatics, for instance, visualize information content per position in DNA or protein sequences, as seen in the figure. Positions with low entropy, high information content show up as tall, clear letters, indicating strong conservation and likely functional importance. High entropy positions appear shorter and more mixed, indicating variability. So even though genomics involves massive, complex data sets, information theoretic measures like entropy, information content, and mutual information help us distinguish meaningful, constrained variation from random background noise, and frame how much genomic data actually contribute to improving clinical decision making. To bring everything together, let's look at how information theoretic measures actually help AI in medicine. First, quantifying confidence. Entropy and related measures let a model express how sure it is about a prediction in a quantitative way. Instead of just saying this is diagnosis A, a calibrated model can say something like this is about 95% probability of diagnosis A. That mirrors how clinicians already think and talk in terms of likelihoods and can make the model's outputs more interpretable and trustworthy as long as these probabilities are well calibrated. Second, identifying risky or uncertain cases. High predictive entropy or high epistemic uncertainty can be used to flag cases where the model is unsure. The system can then route those cases for human review, suggest additional tests, or trigger safety checks. In practice, this becomes a kind of self-triage. Routine, low uncertainty cases are handled with more automation, while ambiguous cases are escalated, improving overall safety. Third, optimizing diagnostics. Using the idea of information gain, formally, mutual information between disease status and test outcomes, an AI-based system can recommend which test is expected to reduce uncertainty the most. Instead of ordering a long list of low-yield tests, the model can suggest the few that are likely to be the most informative for a specific patient. That can reduce cost, shorten time to diagnosis, and align with precision medicine principles. Finally, supporting personalization. As we add more personal data, genomics, biomarkers, wearable data, social media, we can ask, how much does this particular type of data actually reduce uncertainty in predictions? If adding a biomarker or a genomic panel leads to a large reduction in predictive uncertainty, then it is highly informative and may be worth the effort and cost. If it barely changes the model's uncertainty, then it might be a low-value data source for that task. Information theoretic measures give us a way to quantify that contribution rather than relying on intuition alone. Overall, information theory helps medical AI-based systems be smarter, safer, and more transparent. They can express confidence, flag their own weak spots, suggest the most informative next steps, and clarify which data actually add value to patient-specific predictions. Even though information theory gives us powerful tools, actually using them in medicine raises several challenges. First is the communication gap. Concepts like entropy, bits, or mutual information are not part of everyday clinical language. If we tell a clinician that the diagnostic entropy is 1.5 bits, that is not immediately actionable. We need to translate these quantities into forms clinicians already use and understand. Probabilities of outcomes, confidence intervals, risk categories, or clear recommendations. That is as much a human factors and interface design problem as it is a mathematical one. Second, data quality and bias. Information theoretic measures assume that the underlying probabilities are meaningful. In healthcare, data can be systematically biased or incomplete, certain populations underrepresented, missing histories, inconsistent documentation. A model trained on such data might produce very confident predictions that are nonetheless wrong for some groups. Entropy or mutual information computed on these outputs won't reveal the bias on their own. In fact, they can give a misleading sense of precision if the model is confidently wrong. Third, the rare events dilemma. Medicine cares deeply about rare but severe outcomes. A 1% probability of a fatal complication might correspond to low entropy because the model is mostly certain that nothing bad will happen. But clinically, that 1% may still be unacceptable. A pure reduced entropy objective can underweight these low probability, high impact events. We need to combine information theoretic measures with clinical notions of utility, harm, and acceptable risk. Finally, regulatory and workflow issues. Even if we can accurately quantify uncertainty, deciding how to act on it is non-trivial. When should the AI defer and say, I'm not sure? When should a clinician be required to review and override? If the AI signals uncertainty and a clinician ignores it and makes an error, who's responsible? Healthcare regulations, liability frameworks, and institutional policies are still evolving around these questions. So quantifying uncertainty with entropy, KL, and mutual information is only part of the story. The harder layer is integrating these signals into clinical workflows, communicating them in a way that clinicians can use, and aligning them with ethical, legal, and safety requirements in real-world care. To close, let's pull together the main ideas from the lecture. Uncertainty matters. In machine learning and especially in medicine, it is not enough to produce accurate predictions. We also need to understand what we don't know. The distinction between aleatoric uncertainty and epistemic uncertainty helps us see when more data or better models can actually reduce uncertainty and when it's irreducible. Information theory gives us a principled toolbox. Entropy provides a quantitative measure of unpredictability. KL divergence tells us how different one distribution is from another. Mutual information measures how much knowing one quantity reduces uncertainty about another. These are not just abstract definitions, they connect directly to compression, cross-entropy loss, feature selection, active learning, and theoretical notions of learning and generalization. Third, these ideas bridge to practical medical scenarios. We saw how information measures can formalize diagnostic reasoning, entropy to measure how uncertain a differential diagnosis is, KL divergence to quantify how much a specific test result changes our belief, and mutual information to choose which test is expected to be the most informative. We looked at how they apply in medical imaging, longitudinal EHR modeling, and genomics, helping us understand where predictions are reliable, where they are shaky, and how additional data can reduce uncertainty. Fourth, they must be used with care. Information theoretic quantities bring mathematical rigor, but bits by themselves do not tell the whole story. We need good calibration so that probabilities mean what they say, thoughtful communications so that clinicians see uncertainty in a usable form, and awareness of context so that rare but critical events are not downplayed just because overall entropy looks low. Ethical, regulatory, and workflow considerations all shape how these measures can be safely applied. Finally, AI systems move deeper into high-stakes areas like medicine. Combining uncertainty quantification with information theory is key to building systems that are not only accurate but also safe, interpretable, and trustworthy. The most responsible model is not the one that is always confident. It's the one that can recognize and communicate its own uncertainty and work with human experts to manage the risks that remain. That concludes our lecture. I'm Philip Frieda and want to thank you for taking the time to join me today. If you found this lecture helpful, please consider leaving a like and subscribing to the channel for more discussions on AI and machine learning. Also look in the description for a link to Ryan Urbanowicz's channel, which has more lectures from this AI course. I highly appreciate constructive feedback, so please drop your thoughts, questions, or suggestions in the comment section below so we can continue to improve these lectures. Have a great day.